Thank you. Thanks for inviting me. Thanks for coming here. Today I'm presenting my research of the last 3 years on repetition in structures, repetitive structures. Quickly to myself, I am an architect. I finished school in 2008 in Munich. I'm not sure you just said all that. I worked in London and in Munich and also in Shanghai as an architect, and I got interested, or I specialized as a computational designer for complex building envelopes. And so I specialized in the 3D planning of that. And this has become also my topic of research, and we've just recently built this building, this beautiful pavilion, which can be constructed from straight lamellas, and every node is 90 degrees. And I would like to today tell you how I got from one to the other. So when I was working in London on big scale projects, I always had this urge to simplify the construction. So I always try to use the same radius or use the same parts. So when I started researching and teaching at the TU Munich, I wanted to introduce or wanted to investigate this repetition in structures with the students. But most of them didn't know computer parametric modeling. And so what we did, we used a method of research by design, which I think is a very important method for architects to do research with. And I started this project called Experimental Structures, in which the students had to make a module, a 3D module that's very easily fabricated. I mean, we're talking about just simple strips that they can cut by hand. This was supposed to make a module from it, and then add that module together to create a surface. And then we would see what surface they got out of it. And they could do that without the computer because they knew every module should be identical. And we did this, and I'm just going to show you some of these projects, which were at this time very creative and fun, and they gave a variety of solutions. But we will find out later that they are quite, they show some typical principles of repetition in a structure that we will understand later. So over 3 years' time, 2014 to 16, I had this study, and I did a multitude of projects, and I'm just going to show you, I just showed you one of them. I'm just going to show you 3 more that I think quite fascinating. So one student, Marcus, he was called, took my proposal quite seriously to do a repetitive module, and he took a 10 by 10 centimeter cube. And he said, I want to make a double curved surface out of this. Now, this was actually not what I had thought of. I thought that they should make modules that would actually create the curvature. But in his sense, it was actually a very beautiful geometrical study because he got this problem of the gap, right? He had to fill in the gap. So we started looking at this, and we very soon noticed that it was not only the distance between cubes. First we thought just distance on top, distance on bottom. But then we noticed there was actually also, like, of course, a kink in there. And then if you walk along the grid, you start getting a shear between the different modules. And because you get the shear, 2 related modules also are torsioned, especially if they don't run along the center, which along the principal curvature lines. So it was getting quite complex, but he managed to, you know, compute the rings, and we got this beautiful layout of the top and the bottom rings, which basically gave a beautiful tiling pattern in plane. And he constructed this very beautiful, I would say, curved Firendale structure. So another project here by Eleonora. She wanted to do what Frei Otto did, a funicular shell. But again, my course proposal was to use a module. So she didn't want to use continuous lath, but she developed this leaf-like module, which would allow her to have a hinged node in every intersection. And then once she hung that structure up, all the joints would basically change their rotation angle, and she could then just, with a second node here, fix that angle in place. She really just did that, I think, with, with a stapler or something like that. And then she could just turn that structure around, and it would become, for that cardboard paper size, a quite stiff grid shell. And the third project I just want to show you for the creative input is we investigated curved folding. So we looked at what folds do to a structure. You're probably all aware of this, or maybe you've tried it. So if you give the fold a curve, you get a concave and a convex shape of the final module. If you do it twice, you can actually swap and swap, so concave, convex, concave, and you can also do that the other way around. And you can use these folds to manipulate the outside boundary, in this case for a triangle of your curve. So you can really design the tangency of the outside of this module to fit a certain surface, just dependent on how you place the folded creases. And we thought that was very, very interesting. And so we tried to find a logic how to tile a curved surface. And we didn't try that on a freeform surface, but I think it would be possible. But we tried it on a very simple platonic solid. So just a very clear solid that has same sides, same angles everywhere. And I'm using now a cube to explain our logic. So if you heard of platonic solids, you might have heard of the Schläfli diagram, which says how many corners does each polygon have? 4. And how many polygons meet in one corner? 3. So the Schläfli diagram of a cube is 4, 3. And just from these two numbers, you can deduce the curved fold pattern if you want to build this. Because if you know I want to take this node and I want to press it flat into the plane, I will get a node that has 3 polygons meeting, so every node must be 120 degrees. And each polygon has 4 sides, so I will have to take 4 of these. Here I'm taking half one, 1, 2, 3, another half, so that's 4. And so I end up with an incomplete hexagon in plane. And that is actually already the pattern, because if I want to make a curved crease module out of this, I just have to take basically tangential circles to that pattern. And this gap, this incompletion, is exactly what I need to create the double curved module and create the side of the paddle. So this logic works well with not only with cubes, what we did with a tetraeder, with an octaeder, with a dodecaeder and an icosahedron, and we used that also to build a structure which is, I think this one was about 1.50 meters in diameter. So these are just some creative inputs, because now I'm going to get to the boring theoretical part of my research. So I was really intrigued, but I wanted to know, why do some things work better and why do some other works don't? So and from my practical experience, I know we always design a freeform surface as an architect that fulfills the architectural or functional requirements. And then we basically chop it up. We chop it up into the following elements: into panels or faces of a mesh, right? Into edges, or later in the structure, and into nodes. These are the 3 entities we end up with. And most of the time, all of them are different, and all of them have different angles and different sizes. But sometimes they're more equal. And I was wondering, what do these examples have in common, and what do other examples don't have, that they reach repetitivity of these elements? So what I'm going to show you today is a theoretical framework that I came up with, which investigates the geometrical characteristics of such structures, but also the constructive criteria. And I noticed, if you look at both, at how it is constructed and what its geometry is, if you overlay the two, then you can very precisely say why it has repetition or why it doesn't, and why it can be built from the same parts and why not. And this is what I'm trying to explain to you today. And you can use this theory to analyze existing structures very precisely, but you can also use it to study new structures and to invent other structures from it. And we did this, and we invented this grid shell that I've already showed you, and we built it and used this technology. But before I get to the theoretical framework, I have to just cover some of the basic theories. Most of you've probably heard, so I'm just going to run through them. So when I talk about a surface, I'm talking about a 2D array of points. And you can have certain categories of surfaces. You can have traditional, freeform, and physical surfaces. So freeform is basically what we do on the computer, and we can make any shape. And physical surfaces are the ones that are dependent on certain physical or even mathematical principles. So you cannot just design them by yourself. Now, I have any of these freeform surfaces, and then I chop them up, as I said. And there is a very important distinguishment to make. I can chop them up by drawing a curve on the surface. You can imagine a balloon and taking a pen and drawing it on top of that, a continuously curved surface, and then I get a smooth segmentation. Or, on the other hand, on the contrast, I can just draw points on the surface and connect them, and then I get a discrete segmentation of that surface. So that would be a mesh. And of course, in real structures, we have hybrids of those. I would call them semi-discrete or hybrid segmentations that have maybe some straight lines and some curved lines, however that's possible. Well, and of course, these segmentations can be any sort of network. So normally in architecture, we have triangular, hexagonal, and quadrilateral networks. I'm going to skip through the topology. I think everyone is aware of that. What I really want to concentrate today is on smooth segmentations, and there it is important to understand curvature. So I'm going to repeat the very basics. What is curvature? The curvature is the inverse of the radius at a certain point on a curve. And you can measure that anywhere along the curve. And you can even add that up, and then you get this total curvature. So that is as if you take the normal vector on any point on the surface, and you map that onto one point, a unit vector, and then you get all the different orientations of this curve. And if they overlap, they cancel each other out. So the total curvature of this curve is really just that little bit, that little extra curvature in the one direction. That is the total curvature of a planar curve. Now we looked at a curve, now we can look at a surface. What is the curvature of a surface? And here you look at the two principal curvatures, the two maximum curvatures, and you can either multiply them to get the Gaussian curvature, or you can take their average to get the mean curvature. Now, again, I'm going to explain this. Let's say we have a surface, and we can here cut through the normal vector at any point and measure its curvature, and what we will get is the sinus curve. And the sinus curve would have a maximum, which will be, for example, this direction. That's principal curvature 1. And it will have a minimum down here. That's principal curvature 2. And if we multiply both of them, we get the Gaussian curvature. And the average is h. That's the mean curvature. And here, why I'm showing this is because here you can also beautifully see where this normal curvature hits 0. So that's where the orange line is. That is the asymptotic direction. And that's something that that I will come to later as an important part of my research. And again, I want to say, of a surface, if you have a surface, you can measure the total curvature of that surface. So you can measure the Gaussian curvature on any point, and then get the integral of the whole surface. And you can do that also graphically, again, in the same way as the planar curve, as I just showed. So you take the normal vector on every point, you unitize it to 1, and you put it on in a center, and then you get the Gaussian image. It's a sphere which has the image of this curvature here. And the interesting thing is you can imagine like a bed sheet. So if you have a completely positive curvature, you end up with a nice image, or a completely negative curvature, you end up with like an inverted image. But if you have both negative and positive curvature, you end up with like this folded image. It's like a bed sheet folded onto. And the absolute curvature of such a surface is the integral, or the sum of all the negative and the positive curvature, but you can also calculate the absolute total curvature. That's as if you would take the whole bedsheet and take the whole area of that bedsheet. And I want to introduce a third value here, which is basically the footprint. So I'm taking the outline of this image, and I call that the Gaussian footprint, and I will use it later. Now the last theoretical bit, and then we can start with my theoretical framework. Now, if we covered surfaces and we covered curve, and the last theory on curvature that I want to explain is a curve on a surface. Because in that instance, you get the tangent vector of the curve, and you get the normal vector of the surface, and you can combine them to create a coordinate system. It's called the Darboux frame. So let's imagine we are an ant, and we are driving in our car over this surface. If we go up and down, like on a hill, that would be the normal curvature. That means we're rotating around the sideways vector. That's the normal curvature we can deduce. Now, if we actually actively steer left and right, then we rotate around the normal vector of the surface, and that would be the geodesic curvature of that curve. And the last bit is, you can imagine driving, and the car is basically tilting from one side to the other. Then it is rotating around its own tangent vector, and that would be called the geodesic torsion of that curve. So these are three curvatures that I can assign to a curve that lies on a surface. And now let's jump straight into my theoretical framework, because that's pretty much covers most of it. So I looked at these networks on curved surfaces, and I found that there's like, let's say, two main parameters that exist on any network. It's the length of edges between two nodes, and it's the intersection angles of the edges. And of course, the faces you can also define by the shape, let's say the outline, and by their own curvature, but that is more complex. That's not one value, but that's a more complex parameter to define. Now, when you look at smooth segmentations, you get these three extra parameters that I just explained, the curvature parameters of that curve. So the normal curvature, the geodesic curvature, and the geodesic torsion. And the beauty is, when you look at discrete segmentations, you also get three extra angles. And they're not any angles, they're directly related to the curvatures which I just showed you. You can actually calculate from one to the other if you have to. So if you imagine a joint, the normal angle, I called them the same name now, would be this kink angle that you get at a discretized mesh. The geodesic angle would be the difference between a straight line at this point and this extra kink that you get, which is close to the geodesic curvature. And finally, the torsional angle, which is if two panels not meet straight, but they are twisted to each other. So they are exactly related to the three curvatures of the curve. And that is actually it. These are the parameters. I overlaid both of them for any hybrid segmentation, and so I get these parameters. And what I said is, if you want to investigate if a structure is repetitive, you just have to check all these parameters, and if they're all the same, then it also is repetitive. So I got this table, and this table also covers some offsets, by the way, the offset of the node, the offset of the edge, and the offset of the face. Other than that, it's what I just explained. But this is only the geometric part. Now, when you look at an actual structure, you might find that there is a variable geometric angle, for example, but the structure is built from the same elements anyway. So very often you can use the same element even though the geometry is not repetitive. And that's why we have to distinguish three constructive criteria. The first one is very obvious, it's tolerances, right? Even though you might not have the same curvature in every panel, if you just have a little tolerance, you can make them all planar anyway. Or if you can use the same size panels, which they did in the Olympic Stadium in Munich, by just having, you know, a large neoprene gap in between them that serves as a tolerance to do so. The next criteria is hinges, which is also quite obvious. In a joint, if you have varying angles, if you just have a hinge, the joint can just take whatever angle is necessary in that point. You can use the same hinge anyway. And the third one, which is most interesting to me in my research, is deformation. So you can use a flat piece and just form it to whatever curvature you need to. And so what you see down here is these are my geometric parameters, and you see that these criteria directly relate to these geometric parameters. The tolerance kind of are able to verify length or shape. The hinges are able to verify all the angles in the node, and the deformation is able to verify all the curvature of faces and edges. Now, if we look at the curvature, this is especially interesting because we can relate the mathematical curvature directly to the mechanical bending of a beam. And there, any engineer will also look at exactly these three bendings: bending sideways, bending upways, and torsion. And finally, what I want to say about this is normally in mathematics, when we talk about deformation or something, we always try to stay within developable deformation. So we try to have a shape that is developable, because then we say we can deform it. But I want to make the point that it is, of course, also possible to deform something in a non-developable way. For example, by twisting it or by slightly bulging it, if that material is elastic enough to do that. It's all about calculating the stresses. Okay, let's jump in an analysis to understand why I'm doing this complex framework. I used the reticulated dome in Neckarsulm by Schleich-Bergermann. It's a beautiful, actually smooth grid shell on a spherical geometry. And if you look exactly at this pattern, we actually got the geometry from their office and we modeled it precisely, and then we numerically measured every single parameter. And here you can see all the blue ones are constant and all the red ones are variable. And here you can see not only that they are variable, but you can actually see the spectrum. So what is interesting, that the angle between two edges, it's not actually completely smooth like here, but it has a slight kink angle. I don't know if you can tell that. So it's basically smooth on the surface, but there's still a slight kink angle. So we could measure that, and this angle allows the geodesic curvature to be 0. So the lines are actually geodesic lines going from node to node, but then they kink. So the two are basically can be swapped out, which was used here. And then we have the varying intersection angle. And now as a second step, this is the geometric analysis. We can look at the construction analysis, and we can look at how did they actually build that. And if we look at the joints, we can see they had a joint for the intersection, and they actually had a second joint for this kink angle. So they did exactly that. They looked at the different parameters and they made joints right there. And so if we overlay the two analyses, we can see the whole structure could be made from repetitive pieces. The only piece that they actually had to cut individually was the shape of the glass panels. Okay, this is the kind of theory that I did, and I did this, and here now I'm always going to throw in some of my first examples just to see why, just to show why this creative input in the beginning is actually quite relevant, because this is exactly what Eleonora did. She used exactly the same thing. She has no geodesic curvature, but she has that extra kink, and she has a hinge in these things. So this is exactly basically the same strategy used by her. So I did this analysis for a multitude of projects. I didn't do it numerically like I just showed, but more qualitatively. And so that gave me the option of basically really putting in this huge table and putting in what is constant and what is not. And it's very theoretical, I have to say. I'm not going to bore you with this. But it gives you some general tendencies of, you know, if it's a cylinder, you can do more, and like some general, you know, principles of repetitive structures. But what I find way more exciting is to go the other way around. So you can draw the table, and you can say, what if all parameters are the same? Or what if only one parameter is variable? Or what if only two parameters are variable? So you can systematically go through the table. This is, by the way, the table for all smooth segmentation. So I deliberately left out the node angles, which are only present in discrete segmentations. And you can go through that, and you can find the solution for everyone. As you can see, there's a lot of empty lines, because I haven't analyzed all of them. But these are all examples that are part of my thesis. And what you can see here in the beginning, when you have little parameters that are loose, you end up with, you know, spherical or cylindrical. This is a pseudosphere, so very restricted shapes. And the more you let loose, you get into the freeform business. And in between, there are some extra forms like a hyperbolic paraboloid, or, you know, minimal surfaces that have some in-between possibilities. And I think this is what's really interesting about looking at it systematically, that you can really define the design spectrum of repetitive structures, and you can clearly define what is possible if you want to have repetitive parts. So I'm now going to just show you a few of these studies that I used to find out these shapes. The first one is a very simple study. I only looked at the intersection, or the mesh angle, and the length of an edge, and sometimes also if the faces are planar. And I just used a regular mesh, and I threw it onto a surface, and then I checked, for example, in this case, is the length still constant? Yes. Is the mesh actually on the surface, so is the proximity 0? Yes, and then I'm going to color it blue. And if it doesn't, then I'm going to color it gray. And then I get this table, and I get an overview of different parameters and what shapes they can actually make, they can actually form, and which ones they cannot. So this is a discrete quadrilateral mesh. And what I also introduced is red-colored examples. If there was a valid solution, but it was just not fair enough, it was a kind of a crumpled mesh, or the edges were overlaying each other, then I said, generally there is a geometrical solution, but it's not fulfilling the fairness criteria. So I did this for quadrilaterals and hexagonals and triangular meshes. And I just want to point out like two insights I had. The one insight is that triangular meshes are very restricted. Really, all they can really do is, I'm just quickly going to go back, they can really only do cylinders or developable shapes. Any other shape is not possible if you want to have same length or same nodes, because they both exist coherently. So only if you want planarity, then you can do anything with triangles, because any triangle is always planar. But what I noticed when I did this is that, of course, the gray solutions, the solutions that are not valid or don't work, they can also be very beautiful. And if you want to build something with repetitive elements, you should also investigate solutions that don't lie on the surface or that don't fulfill all the criteria. So I think this is an important insight. And the next insight I want to say is also very basic. These are now smooth grids. You can have grids with the same length of edge, and you can have grids that always have the same node. But you cannot have both at the same time. If you want to have a constant node angle and a constant edge length, you're always going to end up in the plane. What is going to happen if you force that is you're going to get this Fisher net effect, I call it. So the edges are going to distort to accommodate the 90-degree angle and at the same time the consistent length. And these are, I would say, solutions that are geometrically indeterminate. Like we don't really know what's happening here, so I wouldn't build on that. But to prove me wrong, this is the first example that I showed, and that's exactly what happened there. He basically used the same length, and he used the tangential or same node, and he did get a double curvature out of it, but just because he has a Fisher net effect all over the place. So I want to show a new study that I based on this, and this one, did I jump before? No. Here I only investigated panels and tolerances between panels. I did this together with Philipp Eversmann, who worked at the ETH at that point. And we took rectangular glass panels that were all the same size, I think 1 by 2 meters, and we tried to So I skipped something because the panels were not in the right order. What I wanted to finish up with this study on my quadrilateral grids is that I realized if you have, for example, same length of edges, you get a varying intersection angle. And I wonder how this variation in the angle is dependent on the overall surface. And what I realized, what I tried, is I took all my solutions and I mapped the Gaussian image, which I explained. And I realized that the value of the Gaussian footprint, which I did before, is directly related to that variation of the angle. This is something I will going to come back to in the next study, which I just started. So I think that the footprint, that means the outline of the Gaussian image, is a very important indicator of repetitive structures. If you have a repetitive parameter, it shows you how much variation you have. Mic check. 1, 2. I think it works. Yeah. So coming from a theoretical network and going to actual built structures is still a long ways. So the first thing that we had to think of is how are we actually going to model and build these lamellas? And the first intuition was we have to make them developable strips, because that's what works best, because they can be laid out flat without any shearing and torsion. And if you do that, you can do that by just calculating the rulings, which are between the normal and the tangent vector. They are directly related to the curvature of the surface. And these rulings, though, they tend to incline. They are never straight, they're always inclined, and the higher the curvature, the more they incline. And so what happens in areas with high Gaussian curvature, you get these inclined rulings, and then your strip will warp. And so even though you have nice 90-degree intersections, every intersection is different because it meets in a curved line. And so we decided that is not the goal of our research. We don't want this to happen. So we modeled our strips along the rulings, which ensured that every intersection is identical and straight. But the strips are now not developable. They are a non-developable deformation. They are twisted. The good thing is, bending around one axis or twisting is the same. It's just stressing the material to some degree, and we can calculate how we stress them directly because of this comparison which I showed you. So there's actually 3 formulas that we use during the design to calculate the stresses. And if they were still in their elastic realm, that means the material could stretch accordingly. We said, fine, then we can do that. And so just to calculate the curvature left and right, the bending, we can use the Euler-Bernoulli formula to do that. And if we want to calculate the twisting, we use 2 formulas actually. We use the Saint-Venant formula to get the shear stresses from that torsion. But additionally, what we have to calculate is the helix torsion. So these are additional normal stresses. And how that happens is, if you imagine you have a lamella and you twist it really far, and we're twisting it by up to 60 degrees per meter, then the outer fibers of that lamella get longer, and the inner fibers stay the same length. So you get this discrepancy in length. And so you get a stretching of the outer fibers and a compression of the inner fibers, and you get this stress distribution. And there's actually a formula that you can use to calculate that and get very quick results on the stresses in the lamella. So with that knowledge, we designed pavilions and prototypes that were inside the elastic realm. And then there's 2 more constructive developments that happened. The first one is that we didn't use one lamella. I mean, the first intuition is to just use one lamella, but the problem is you can bend it really nicely, you can set it up, and once it acts as a grid shell and there's pressure on it, it just buckles. It can't take a lot of loads. So what we do is we use 2 lamellas and we bend them each individually, and once we have the nice curvature, then we couple them together to become one strong beam. And that's a strategy that's not new. Again, Frei Otto used the same strategy in his Gridshell in Mannheim, but just in the other direction. And the second development that happened is that we realized we don't want to put up the asymptotic lamellas in space, like between frames. It's way too complex. So what we're going to do is we're going to prefabricate the segments flat, as you can see here. And it's interesting because if they lie flat, their angles are not 90 degrees. And then we can just deform them, and they will automatically follow a compliant mechanism. They can't go anywhere else but go up until their angles are 90 degrees. And then we can fix the angle at 90 degrees, and we will end up with the correct shape. Why I'm saying it like that is that it was when we first did it, it was quite a surprise. It's enough that you just push down one corner and the whole structure will follow this mechanism and it will go into the correct shape. That means you don't need any form scaffolding. You can just push it until it's 90 degrees, fix the nodes, and you will have the correct shape. So with this constructive and geometric methods, we started designing. We had this beautiful courtyard, and we designed a freeform surface that would fit nicely into the islands and surround a tree in its center. And then we refined that surface to be of minimal properties, minimal surface properties, and built the asymptotic network on that. And the rest is just creating the lamellas, the edges, edge lamellas and supports, and of course the diagonal grid to triangulate that grid shell. So we end up with this triangulated network. We have two singularities here. All the joints are identical, and we're just built from this set that was also prefabricated and are attached with one bolt through the center. And this is what we fabricated, and this is what the metal, what we got supplied by the metal company. This is the complete pavilion lying in front of us. What I have to say, what's missing are these curved edge lamellas. They had to be milled curved. But I think this was quite fascinating. It all fit on a very small, it was transported on a tiny volume because they're just stacked. And they're just different lengths between the nodes. Everything else is just straight and repetitive. And so the processes of building the pavilion were quite simple. All the nodes were just prefabricated identically at 90 degrees. The lamellas were slotted together by hand and then bolted on planar to 9 segments. And then we just deformed these segments into the curved geometry. And once it had reached that, we fixed the nodes tightly and we added some extra edge supports. So these 9 segments were brought to site and then were combined like a large 3D puzzle. They were just overlapped and bolted together. And finally, we added the diagonal bracing that would stiffen that structure and create a load-bearing grid shell. So the whole grid shell has a high curvature, and it was a real challenge to find a minimal surface that would also kind of have the characteristics of a funicular form. So we really tried to have these arches so that it would nicely carry the loads down into the supports. Finally, what I want to say is such a grid can be easily paneled as well. We have paneling solutions, but it is exactly bisecting to the principal curvature lines. So that means you can put panels, if you put them at 45-degree angle, you can put planar square panels of glass on this structure. So these are just some pictures from the summer with the students are enjoying it. The tree is still growing, and we're liking it a lot. And we just last week we got a first phone call from a client who wants a canopy roof for a hotel built in the same with the same strategy. So with this, I would like to end my talk, and I would just like to conclude what I find the most important insights. For one, if you look at the geometric parameters and at the constructive parameters, you can very clearly define if you can get a repetitive structure or not. And what I found most intriguing is that the repetition is not limited to cylinders or to simple shapes, but you actually have a great variety of design still in that repetition. And not only that, you can also look at strategies that are not fulfilling my theoretical framework, like going out of the shape or taking S-curves, and you can get to other beautiful solutions that I might not know yet. And finally, you can use this theoretical framework not only to design a theoretical network, but you can really find structural solutions of bend and elastic gridshells and really apply it when constructing a structure. With that, I would like to thank you for your attention. Thanks.